The Structure of Scientific Revolutions is a book about the history of science by philosopher Thomas S. Kuhn. Its publication was a landmark event in the history, philosophy, and sociology of scientific knowledge and triggered an ongoing worldwide assessment and reaction in, and beyond, those scholarly communities. Kuhn challenged the then prevailing view of progress in normal science. Normal scientific progress was viewed as development by accumulation of accepted facts and theories. Kuhn argued for an episodic model in which periods of such conceptual continuity in normal science were interrupted by periods of revolutionary science. The discovery of anomalies during revolutions in science leads to new paradigms. New paradigms then ask new questions of old data, move beyond the mere puzzle-solving of the previous paradigm, change the rules of the game and the map directing new research. For example, Kuhn's analysis of the Copernican revolution emphasized that, in its beginning, it did not offer more accurate predictions of celestial events, such as planetary positions, than the Ptolemaic system, but instead appealed to some practitioners based on a promise of better, simpler, solutions that might be developed at some point in the future. Kuhn called the core concepts of an ascendant revolution its paradigms, and thereby launched this word into widespread analogical use in the second half of the 20th century. Kuhn's insistence that a paradigm shift was a melange of sociology, enthusiasm and scientific promise, but not a logically determinate procedure, caused an uproar in reaction to his work. Kuhn addressed concerns in the 1969 postscript to the second edition. For some commentators, Kuhn's book introduced a realistic humanism into the core of science, while for others the nobility of science was tarnished by Kuhn's introduction of an irrational element into the heart of its greatest achievements. History. The Structure of Scientific Revolutions was first published as a monograph in the International Encyclopedia of Unified Science, then as a book by University of Chicago Press in 1962. In 1969, Kuhn added a postscript to the book in which he replied to critical responses to the first edition. A 50th anniversary edition was published by the University of Chicago Press in April 2012. Kuhn dated the genesis of his book to 1947, when he was a graduate student at Harvard University and had been asked to teach a science class for humanities undergraduates with a focus on historical case studies. Kuhn later commented that until then, I'd never read an old document in science. Aristotle's physics was astonishingly unlike Isaac Newton's work in its concepts of matter and motion. Kuhn concluded that Aristotle's concepts were not bad Newton, just different. Synopsis. Basic approach. Kuhn's approach to the history and philosophy of science focuses on conceptual issues like the practice of normal science, influence of historical events, emergence of scientific discoveries, nature of scientific revolutions and progress through scientific revolutions. What sorts of intellectual options and strategies were available to people during a given period? What types of lexicons and terminology were known and employed during certain epochs? Stressing the importance of not attributing traditional thought to earlier investigators. Kuhn's book argues that the evolution of scientific theory does not emerge from the straightforward accumulation of facts, but rather from a set of changing intellectual circumstances and possibilities. Such an approach is largely commensurate with the general historical school of nonlinear history. Historical examples of chemistry. Kuhn explains his ideas using examples taken from the history of science. For instance, at a particular stage in the history of chemistry, some chemists began to explore the idea of atomism. Many substances, when heated, have a tendency to decompose into their constituent elements, and often these elements can be observed to combine only in set proportions. At one time, a combination of water and alcohol was generally classified as a compound. Nowadays it is considered to be a solution, but there was no reason then to suspect that it was not a compound. Water and alcohol would not separate spontaneously, nor will they separate upon distillation. Water and alcohol can be combined in any proportion. A chemist favoring atomic theory would have viewed all compounds whose elements combine in fixed proportions as exhibiting normal behavior, and all known exceptions to this pattern would be regarded as anomalies whose behavior would probably be explained at some time in the future. On the other hand, if a chemist believed that theories of the atomicity of matter were erroneous, then all compounds whose elements combined in fixed proportions would be regarded as anomalies whose behavior would probably be explained at some time in the future, and all those compounds whose elements are capable of combining in any ratio would be seen as exhibiting the normal behavior of compounds. Nowadays the consensus is that the atomist's view was correct. But if one were to restrict oneself to thinking about chemistry using only the knowledge available at the time, either point of view would be defensible. The Copernican revolution. A famous example of a revolution in scientific thought is the Copernican revolution. In Ptolemy's school of thought, cycles and epicycles were used for modeling the movements of the planets in a cosmos that had a stationary Earth at its center. As accuracy of celestial observations increased, complexity of the Ptolemaic cyclical and epicyclical mechanisms had to increase to maintain the calculated planetary positions close to the observed positions. Copernicus proposed a cosmology in which the Sun was at the center and the Earth was one of the planets revolving around it. For modeling the planetary motions, Copernicus used the tools he was familiar with, namely the cycles and epicycles of the Ptolemaic toolbox. Yet Copernicus' model needed more cycles and epicycles than existed in the then current Ptolemaic model, and due to a lack of accuracy in calculations, his model did not appear to provide more accurate predictions than the Ptolemy model. Copernicus' contemporaries rejected his cosmology, and Kuhn asserts that they were quite right to do so. Copernicus' cosmology lacked credibility. Kuhn illustrates how a paradigm shift later became possible when Galileo Galilei introduced his new ideas concerning motion. Intuitively, when an object is set in motion, it soon comes to a halt. A well-made cart may travel a long distance before it stops, but unless something keeps pushing it, it will eventually stop moving. Aristotle had argued that this was presumably a fundamental property of nature. For the motion of an object to be sustained, it must continue to be pushed. Given the knowledge available at the time, this represented sensible, reasonable thinking. Galileo put forward a bold alternative conjecture. Suppose, he said, that we always observe objects coming to a halt simply because some friction is always occurring. Galileo had no equipment with which to objectively confirm in his conjecture, but he suggested that without any friction to slow down an object in motion, its inherent tendency is to maintain its speed without the application of any additional force. The Ptolemaic approach of using cycles and epicycles was becoming strained. There seemed to be no end to the mushrooming growth in complexity required to account for the observable phenomena. Johannes Kepler was the first person to abandon the tools of the Ptolemaic paradigm. He started to explore the possibility that the planet Mars might have an elliptical orbit rather than a circular one. Clearly, the angular velocity could not be constant, but it proved very difficult to find the formula describing the rate of change of the planet's angular velocity. After many years of calculations, Kepler arrived at what we now know as the law of equal areas. Galileo's conjecture was merely that, a conjecture. So was Kepler's cosmology. But each conjecture increased the credibility of the other, and together, they changed the prevailing perceptions of the scientific community. Later, Newton showed that Kepler's three laws could all be derived from a single theory of motion and planetary motion. Newton solidified and unified the paradigm shift that Galileo and Kepler had initiated. Coherence. One of the aims of science is to find models that will account for as many observations as possible within a coherent framework. Together, Galileo's rethinking of the nature of motion and Kepler's cosmology represented a coherent framework that was capable of rivaling the Aristotelian Ptolemaic framework. Once a paradigm shift has taken place, the textbooks are rewritten. Often the history of science too is rewritten, being presented as an inevitable process leading up to the current, established framework of thought. There is a prevalent belief that all hitherto unexplained phenomena will in due course be accounted for in terms of this established framework. Kuhn states that scientists spend most of their careers in a process of puzzle solving. Their puzzle solving is pursued with great tenacity, because the previous successes of the established paradigm tend to generate great confidence that the approach being taken guarantees that a solution to the puzzle exists, even though it may be very hard to find. Kuhn calls this process normal science. As a paradigm is stretched to its limits, anomalies, failures of the current paradigm to take into account observed phenomena, accumulate. Their significance is judged by the practitioners of the discipline. Some anomalies may be dismissed as errors in observation, others as merely requiring small adjustments to the current paradigm that will be clarified in due course. Some anomalies resolve themselves spontaneously, having increased the available depth of insight along the way. But no matter how great or numerous the anomalies that persist, Kuhn observes, the practicing scientists will not lose faith in the established paradigm until a credible alternative is available. To lose faith in the solvability of the problems would in effect mean ceasing to be a scientist. In any community of scientists, Kuhn states, there are some individuals who are bolder than most. These scientists, judging that a crisis exists, embark on what Thomas Kuhn calls revolutionary science, exploring alternatives to long-held, obvious-seeming assumptions. Occasionally this generates a rival to the established framework of thought. The new candidate paradigm will appear to be accompanied by numerous anomalies, partly because it is still so new and incomplete. The majority of the scientific community will oppose any conceptual change, and, Kuhn emphasizes, so they should. To fulfill its potential, a scientific community needs to contain both individuals who are bold and individuals who are conservative. There are many examples in the history of science in which confidence in the established frame of thought was eventually vindicated. It is almost impossible to predict whether the anomalies in a candidate for a new paradigm will eventually be resolved. Those scientists who possess an exceptional ability to recognize a theory's potential will be the first whose preference is likely to shift in favor of the challenging paradigm. There typically follows a period in which there are adherents of both paradigms. In time, if the challenging paradigm is solidified and unified, it will replace the old paradigm, and a paradigm shift will have occurred. Phases. Chronologically, Kuhn distinguishes between various phases. Phase 1. It exists only once and is the pre-paradigm phase, in which there is no consensus on any particular theory, though the research being carried out can be considered scientific in nature. This phase is characterized by several incompatible and incomplete theories. If the actors in the pre-paradigm community eventually gravitate to one of these conceptual frameworks and ultimately to a widespread consensus on the appropriate choice of methods, terminology and on the kinds of experiment that are likely to contribute to increased insights, Phase 2. Normal science begins, in which puzzles are solved within the context of the dominant paradigm. As long as there is consensus within the discipline, normal science continues. Over time, progress in normal science may reveal anomalies, facts that are difficult to explain within the context of the existing paradigm. While usually these anomalies are resolved, in some cases they may accumulate to the point where normal science becomes difficult and where weaknesses in the old paradigm are revealed. Phase 3. This phase is a crisis. Crises are often resolved within the context of normal science. However, after significant efforts of normal science within a paradigm fail, science may enter the next phase. Phase 4. Scientific revolution is the phase in which the underlying assumptions of the field are re-examined and a new paradigm is established. Phase 5. Post-revolution. The new paradigm's dominance is established and so scientists return to normal science, solving puzzles within the new paradigm. A science may go through these cycles repeatedly, though Kuhn notes that it is a good thing for science that such shifts do not occur often or easily. Incommensurability. According to Kuhn, the scientific paradigms preceding and succeeding a paradigm shift are so different that their theories are incommensurable. The new paradigm cannot be proven or disproven by the rules of the old paradigm, and vice versa. The paradigm shift does not merely involve the revision or transformation of an individual theory, it changes the way terminology is defined, how the scientists in that field view their subject, and, perhaps most significantly, what questions are regarded as valid, and what rules are used to determine the truth of a particular theory. The new theories were not, as the scientists had previously thought, just extensions of old theories, but were instead completely new worldviews. Such incommensurability exists not just before and after a paradigm shift, but in the periods in between conflicting paradigms. It is simply not possible, according to Kuhn, to construct an impartial language that can be used to perform a neutral comparison between conflicting paradigms, because the very terms used are integral to the respective paradigms, and therefore have different connotations in each paradigm. The advocates of mutually exclusive paradigms are in a difficult position. Though each may hope to convert the other to his way of seeing science and its problems, neither may hope to prove his case. The competition between paradigms is not the sort of battle that can be resolved by proofs. Scientists subscribing to different paradigms end up talking past one another. Kuhn states that the probabilistic tools used by verificationists are inherently inadequate for the task of deciding between conflicting theories, since they belong to the very paradigms they seek to compare. Similarly, observations that are intended to falsify a statement will fall under one of the paradigms they are supposed to help compare, and will therefore also be inadequate for the task. According to Kuhn, the concept of falsifiability is unhelpful for understanding why and how science has developed as it has. In the practice of science, scientists will only consider the possibility that a theory has been falsified if an alternative theory is available that they judge credible. If there is not, scientists will continue to adhere to the established conceptual framework. If a paradigm shift has occurred, the textbooks will be rewritten to state that the previous theory has been falsified. Kuhn's opinion on scientific progress. The first edition of SSR ended with a chapter titled Progress Through Revolutions, in which Kuhn spelled out his views on the nature of scientific progress, since he considered problem-solving to be a central element of science. Kuhn saw that for a new candidate paradigm to be accepted by a scientific community, first, the new candidate must seem to resolve some outstanding and generally recognized problem that can be met in no other way. Second, the new paradigm must promise to preserve a relatively large part of the concrete problem-solving activity that has accrued to science through its predecessors. Overall, Kuhn maintained that the new paradigm must also solve more problems than its predecessor, which therefore entailed that the number of newly solved problems must be greater than those solved in the old paradigm. In the second edition of SSR, Kuhn added a postscript in which he elaborated his ideas on the nature of scientific progress. He described a thought experiment involving an observer who has the opportunity to inspect an assortment of theories, each corresponding to a single stage in a succession of theories. What if the observer is presented with these theories without any explicit indication of their chronological order? Kuhn anticipates that it will be possible to reconstruct their chronology on the basis of the theory's scope and content. Because the more recent a theory is, the better it will be as an instrument for solving the kinds of puzzle that scientists aim to solve. Kuhn remarked, "That is not a relativist position, and it displays the sense in which I am a convinced believer in scientific progress, influence." In 1987, The Structure of Scientific Revolutions was reported to be the 20th century book most frequently cited in the period 1976 to 83 in the arts and the humanities. Philosopher Michael Ruse writes that it discredited the ahistorical, prescriptive approach to the philosophy of science of Ernest Nagel's The Structure of Science. The changes that occur in politics, society and business are often expressed in Kuhnian terms. However poor their parallel with the practice of science may seem to scientists and historians of science, the terms paradigm and paradigm shift have become such notorious clichés and buzzwords that they are viewed as effectively devoid of content.